You are welcome to day 3 of the training session on understanding the basics of centrifugal pumps from detail engineering perspective. And I really appreciate those that have been following us up from day 1, day 2, and today being day 3. And I hope you have been enjoying the pump series. So today we also have an interesting, areas of centrifugal pumps that we'll be looking at. So if this is the first time you're coming across the channel or you are yet to subscribe to the channel, please don't forget to click the subscribe button and then press the bell notification button so that you can always get notifications by the time we put different videos, different training tutorials on different rotating equipment or static equipment on this channel. So for tonight, we are going to be looking at what we have, and that is in continuation of the understanding of centrifugal pumps, basics of centrifugal pumps from detail engineering perspective. We are going to be looking at another interesting area as far as centrifugal pump is concerned. So we are going to be looking at net positive suction head. Net positive suction head. During our day 2 session, we spoke extensively on the concept to occur in as in your centrifugal pump operation. So you have to put a lot of things into consideration by the time you are doing detail engineering or you are doing a technical evaluation of your pumping system, so that you can take note of all these terminologies, right? Such as the MPS and MPSH. So tonight we are going to move straight. There are two two considerations for as far as net positive suction head is concerned. We have a concept called the MPSHA, which is the net positive suction head available, right? MPSHA is the net positive suction head available. Then we also have another concept of net positive suction head, which is the MPSHR. So in today's session, we are going to be looking at what MPSHA is all about. How do you determine MPSHA for a given pumping system, and what do you understand by MPSHR, which is the net positive suction head required. So we are going to be looking at all this, as we move on in today's session, right? So starting with NPSHA. NPSHA is simply net positive suction head available. There is no way you will talk about centrifugal pumping system without mentioning MPSHA, right? And MPSHA is nothing but the energy or the head available at your pump suction to prevent cavitation in a pump. Don't forget I said that centrifugal pumps generally, they are not capable of handling large quantities of vapor. So your pumping's external suction system it's a must. It has to be designed in such a way that it must provide sufficient absolute pressure, absolute head, absolute energy, right? To prevent any form of vaporization, to prevent any form of flashing in the impeller by the time the pump is put into operation. Because if this is not done, if this energy is not enough, if this pressure at your external junction system is not sufficient, right, to prevent any form of vaporization, you are calling for what? You are calling for cavitation in your pumping system, which will ultimately cause various damage to the impeller. Not only that, it will reduce the performance of your pump in terms of the developed head capability of the pump. There will be a drastic reduction in the pump's head developed capability. And not only that, there is going to also be a reduction in the pump capacity. And when all this are happening inside your pump, you will see it being manifested into high level of noise or high vibration. That's why you see, when you measure the vibration, or you measure the noise, or you just stand close to some pumps undergoing vibration, cavitation, you will see that a lot of noise will be coming out from the pump, or the pump will be vibrating excessively. So it simply means that such types of pump is undergoing, or cavitation is already taking place inside that pump. So now, to avoid all this, you need to make enough energy available at your pump junction. So that MPSHA is that head, is that energy that is available at the pump junction to prevent what? To prevent cavitation in your pump. And we'll be looking at, in the course of the training session for today, we'll be looking at how do you determine MPSHA, how do you determine net positive suction head available for your pumping system, right? Okay, so I mentioned that MPSHA is actually a characteristic of your system. It's a characteristics of what you have in your plant. It's a characteristics of your system. All right, and it's a function of the system configuration on the suction side of the pump. So you are responsible as the process engineer from the vendor side, right, or the machinery engineer, or the rotating equipment engineer from the client side. In this case now, from the client side, I repeat, from the client side, right, to determine or to calculate your MPSHA, because it is your system characteristics, because your MPSHA will be furnished to the vendor, right, so that the vendor will prepare their own MPSHR, which we will also be looking at. So it is very important as a process engineer to be able to do what? To be able to determine how MPSHA for a particular system that you have in your plant can be obtained. And don't forget, I said MPSHA is a characteristics of what? Of your system, right? Is a characteristics of the client system. So if you're on the client side, you should have a basic knowledge of how MPSHA, which is the net positive suction head available, can be calculated. Before we go into that, let's look at the other end of the MPSH, which is the net positive suction head required. That is the MPSHR. MPSHR is that positive head that is required at, you see, the pump junction to overcome any form of pump internal losses. That head required, that energy required at the pump junction to do what? To overcome pump internal losses is your NPSHR. So it is very important for you to be able to differentiate between MPSHA and MPSHR. We said MPSHA is that energy available at your pump junction to do what? to prevent cavitation. Now, we said MPSHR is that positive head required at the pump junction to overcome any form of pump internal losses. Don't forget I mentioned that MPSHA is your system characteristics. Meanwhile, MPSHR is a characteristic of the pump that you need to be very familiar with. The pump manufacturers would determine by test the MPSHR at various capacities for a particular pump. At the same time, the MPSHA, which is the net positive suction head available, will be calculated by the process engineer or by the machinery engineer from the client side. All right. So for cavitation free operation, the MPSHA obtained as a characteristic of your system must be equal or exceed the MPSHR, which is determined by tests at various capacities for a particular pump by the pump vendor. So for a cavitation free operation, your MPSHR must exceed the your MPSHA, which is the net positive suction head available, must exceed the net positive suction head required at the desired capacity. So no engineer wants to be responsible for installing a noisy or a slow or damaged pump. You don't want to be responsible for that. So that is why it is very important. It is critical to get what? The MPSHR value determined by test characteristics be determined, right? Which you obtain, right? You have to ensure that your MPSHA calculated for your system must be adequate to cover that requirement. So regardless of what the MPSHR obtained by the vendor, right, or obtained from the vendor, your own MPSHA, right, it is critical to get that MPSHA, which is your system characteristics. That difference must be at least 0.6 meter. So the difference between your MPSHA and your MPSHR, in some projects they put that difference for cavitation free operation. You can put it at, say, between 0.8 meter to 1 meter. So it is very important for cavitation free operation, your MPSHA has to be greater than what? Has to be greater than your MPSHR. Don't forget I said your MPSHA is a characteristic of your system. Now let's continue. Now the question now is, how do you determine, how do you do what? How do you calculate MPSHA? Because I mentioned to you that your MPSHA is a characteristics of your system. So it is very important that as a process engineer or as the rotating equipment engineer, carrying out detailed engineering for any centrifugal pump under any project. So you should be able to calculate your MPSHA, which is that energy, which is that head available at your pump junction to do what? To prevent cavitation, right, for your pump. So MPSHA is obtained by this expression. By this expression, MPSHA is the net positive suction head available, which equals to HA plus or minus HZ minus HF plus HV minus HVP. Then I'm going to explain what each of these denotes. Your HA is that absolute pressure on the surface of the liquid in the supply tank. Your HA is that's absolute pressure on the surface of the liquid in the supply tank. So HA typically is the atmospheric pressure, of course, for a vented supply tank. HA typically is the atmospheric pressure for a vented supply tank, but it can be different for closed tanks. Your HA is always positive. Take note. I said HA is typically atmospheric pressure for a vented supply tank, but it can be different for a closed tank, and HA will always be what? Positive. So if you are to use HA, right, in this expression, you have to convert it into what? Into meter, because MPSHA is obtained in a meter. So each of these should be obtained in meter. So there is a relationship between pressure in kg per centimeter square and your head in meter. You will see it in the course of the training session by the time we start some detailed calculations, right? So that is that about HA. Now the next would now be plus or minus. Now it is plus if it is a positive suction system. A positive suction system is that system where you have your suction tank, at or above your pump center line, right? A positive suction system is that pumping system where you have your what? Your supply tank at the pump or above the pump center line. So if it is a positive suction system, you are going to have HA, which is that absolute pressure on the surface of the liquid, plus. But if it is a negative suction system, a negative suction system is that system where you have your supply tank below the pump center line, say a pump drawing liquid from a well, right, or from a reservoir. So for a negative suction system like that, you have your HA, which is the absolute pressure, which typically is an atmospheric pressure for a vented supply tank. So if it is a positive suction, you will use plus. But if it is a negative suction system, you use the minus symbol. Now, HZ, the supply tank, and the center line of the pump. By the time we'll start some calculations, you will see. So that distance between the surface of the liquid in your supply tank and the center line of the pump is your HZ, right? Now, it can be positive when the liquid level is above the center line of the pump. And of course, it can be called static head for a positive suction system. And I mentioned that it can be negative when the liquid level is below the center line of the pump, which you call negative suction system or suction lift. All right. So your HA, for a positive suction system, you have HA plus that vertical distance between the surface of your liquid in the supply tank and the center line of the pump. It will be minus, it will be HA minus HZ if it is a suction lift system or a negative suction system. Now, the next is your minus HF. Your HF, we spoke extensively on this during the day 2 session. So I will want you to go over that day 2 session again, because as we progress, the thing will be getting more very interesting, right? It will be getting more interesting, and then you need to be familiar with some of the things we have treated in the past. Now, your HF is that frictional losses or frictional head loss in your suction piping. If you recall, during the day 2, we said how the frictional losses is calculated is that your friction losses is that sum of the fittings head loss and the straight run head loss. So we look at how the fittings head loss is calculated using the k-value method, and we also look at the way the straight run head loss is calculated. So that sum of the fittings head loss and the straight run head loss is what gives you your frictional head losses. So minus your HF, once you have calculated that, plus, of course, plus your HV. Your HV is actually what? Is actually the velocity head. The velocity head at the pump suction port. The velocity head at the pump suction port. And this is also very important for me to mention to you that often is not included. It can be ignored as it is normally quite small. So in some text or online, when you check, you will see that your MPS HA will just be expressed as HA plus or minus HZ minus HF. Then this will be ignored because it's usually quite small. But meanwhile, your HV is that velocity head, but it is negligible. Minus your HVP. Your HVP is the absolute vapor pressure of the liquid at the pumping temperature. For every fluid, there will always be the vapor pressure at your pumping temperature, which you must have specified on your data sheet. So your vapor pressure has to be subtracted in the end to make sure that that inlet pressure stays above the vapor pressure. Remember, I mentioned during the day 2, as the temperature goes up, because by the time your pump is running, the temperature will be going up. So does the vapor pressure. So please, you also need to take note of what? You also need to take note of the unit, because if your vapor pressure is in kg per centimeter square, for you to use it in this expression to determine your MPSHA, right? You have to convert them to meter. So your HA, which is the absolute pressure on the surface of the liquid, has to be in meter. Your HZ, which is that vertical distance between the surface of the liquid at your supply tank to the pump center line, has to be in meter. Your frictional head loss, which is the sum of the fittings head loss or the straight run head loss, and your velocity head, which is usually ignored because it is quite very small and it has no effect on your MPSHA. Then minus your vapor pressure data sheet for the vendor to determine their own MPSHR by test. So when they supply the mechanical data sheet, which contains some of the mechanical features, right, of that particular equipment. So one of the things that you need to check is the margin between your MPSHA and the MPSHR. Don't forget I said your MPSHA must exceed your MPSHR. So usually, at least that difference has to be at least 0.6 meter. In your own project or in your company, you might specify, depending on the project, can say 0.8 meter. All this is just to do what? To prevent cavitation, from occurring in your pump. All right. So that is that about the MPSHA. Now, for a detailed calculation on MPSHA, I've actually put on my channel some of different cases, right? Different cases, of MPSHA calculations. So you can always just go through the channel and look for a topic where I put understanding MPSHA calculations. So you see different calculations that I have put based on different process parameters, based on different systems. So you can have a better understanding of what MPSHA calculation is. So now next we'll be looking at pump curve, centrifugal pump curve. Usually when a vendor submits their mechanical data sheet for a centrifugal pump, the MD, which is the mechanical data sheet, is accompanied with a curve, which some of you must have seen, and that is a pump curve. It is very important for you to be able to do what? To be able to interpret some of the information available on what? On the pump curve. Very, very important for you to be able to do what? For you to be able to interpret some of the information available on the pump curve, and for you to understand some of the terms available on the pump curve. All right, because it is one of the documents you are going to use to be able to do a thorough technical evaluation of different offers received from different vendors. So a pump curve is nothing but a graphical representation of the overall pump performance, you see, based on testing conducted by the manufacturer. So it is the pump manufacturer that will furnish you with the pump curve, and that pump curve is the graphical representation, like you can see, right? That graphical representation of the overall pump performance based on the testing they have conducted, by the manufacturer. So each pump, we have different hydraulics and we show different performance, and ultimately each pump, we have different pump curves. So you cannot use a pump curve for a pump at plant A and use that same pump curve for another pump in plant B. No, each pump will have their different hydraulics and they will show what? Different performance. All right, so now looking at various parameters available on the pump curve. So the number one parameter that how you will see when you see any pump curve, right? The two essential parameters you will see first will be your flow and the head. The flow is represented on the horizontal axis, right? While your head will be represented, you see, on the vertical axis. In this case, is that differential head, which can be expressed in meter or in feet. All right, your flow can be expressed in cubic meter per hour or liter per second or what? Or gallon per minute. That pump flow on another pump curve, instead of flow, you can see capacity is still the same thing. So you can see pump capacity on the horizontal axis, or you see your pump head or pressure on the what? On the vertical, right? In unit time. While that head is the differential pressure, is that differential pressure difference, which is that difference between the pump outlet pressure and inlet pressure in terms of liquid column. Is just like what I explained to you during the day 2. That's your differential head, is that total head requirement, which is plotted along the vertical axis. Don't forget I mentioned that total head requirement, which is on the vertical axis, is expressed in meter, while your flow or your capacity is expressed in what? In cubic meter or liter per second or gallon per minute, as you can see here. All right, now we have other parameters on the pump curve, such as, of course, you can have the best efficiency point, you can see shut off head, different parameters. You can see efficiency, you can see pump, You can see power, you can see minimum allowable flow, you can see run out flow, you can see maximum allowable flow, you can see different curves, about 3 curves. The rated impeller diameter curve. Usually when a pump manufacturer supply you or furnish you with a pump curve, it comes with 3 impeller diameter curve. You will have the maximum impeller diameter curve, and at the same time you have rated impeller diameter curve. You will have minimum impeller diameter curve. Now the question is, you have to be able to do what? You have to be able to read this pump curve. You have to be able to study. You have to be able to interpret some of the information available on the pump curve. Now, basically, a pump curve demonstrates how it performs. A pump curve, a particular pump curve will demonstrate how the pump will perform at any point in unit range. Now, if you look critically at the pump curve, if you look at the flow increase from this point, from 0, increase, if it is in the range of 10 cubic meter per hour, can be 10, 20, 30, 40, 50. It increases as you move from the left side towards the right end like this. So it increases. Now, look at your head. From this 0, your head increases towards the vertical axis. Now, when you look at this pump curve for a rated impeller diameter, now, what do you think happens? As your flow is increasing, say you have your flow around somewhere here, say it is 50 cubic meter per hour. If you trace this up, now the differential head, to obtain the differential head where it touches the rated impeller diameter curve, right? You will trace it towards the vertical axis. That point here will be your differential head, will be that your total head requirement. So if you look critically, as your flow is increasing for a given centrifugal pump curve, what do you think happens to your differential head? Your differential head is reducing as your flow or as the pump capacity is increasing. All right, same way as your pump flow is reducing, what do you think is happening to the pump differential head? The pump differential head, or the total head requirement, is what? Is increasing. So basically, a centrifugal pump curve will demonstrate how the pump will perform at any unit range. So you can understand this from the following arbitrary performance curve, like I've explained. The flow is recorded on the horizontal axis, just like you can see here, while all other parameters are shown on the vertical axis. Parameters like the power, the MPSHR, all right, the shut-off head, your differential head, they are shown on the vertical axis, right? Now, if you look critically, I mentioned as your flow is increasing, same way your differential head is decreasing because of the shape of the pump curve. This is how the shape of the pump curve looks like for either a rated impeller diameter curve or the maximum impeller diameter curve. So if as the flow is increasing, your differential head is what? Is decreasing. As your flow is reducing, that is the general performance. That is how centrifugal pump behaves. So when the flow is 0, what do you think happens? The differential head generated by a particular centrifugal pump is going to be maximum at a 0 flow. This point is called the shut-off head. So At a zero flow with a maximum head, that point is called what? A shut-off point. A shut-off point, referred to as the shut-off head. Now, on the other side, on the opposite side, when a pump handle maximum flow, that is, as the flow is increasing, and it gets to what? The maximum flow. What do you think happens? From the behavior of the centrifugal pump with respect to the pump curve, right, is going to produce minimum head at the maximum flow. The centrifugal pump will produce what? Minimum head at the maximum flow. At that point of the flow, it is called run-out point, run-out flow. So it is not ideal to operate centrifugal pump at these two extremes. So it is not ideal to run centrifugal pump near this region. The region of what? The region of zero flow or the region of run-out flow. Alright, so you can see that differential head is somehow inversely proportional for any pump with respect to the flow rate. So as the flow rate or the pump capacity is increasing, the differential head is reducing. Now, same way as your what? Your pump capacity or your pump flow rate is reducing, your differential head or that total head requirement is what? Is also going higher. Now, it's also very important if you look at the efficiency curve. This is also on the pump curve. You will also have an efficiency curve. Don't forget, I mentioned that it is not ideal to run a centrifugal pump at these two extremes of zero flow or the run-out flow. Alright? Now, if you look at the efficiency curve, look at the shape of the efficiency curve. On the efficiency curve, you will see a point like this, denoted as the best efficiency point. Now, that best efficiency point is the flow rate at which the pump has the maximum efficiency. So, meaning that on the efficiency curve, if you look at that point, that point on the efficiency curve, right, where you have the maximum efficiency, and you trace it down towards the horizontal axis of the pump curve, whatever flow rate that you obtain is that flow rate at which the pump, right, has the maximum efficiency, and that is called the best efficiency point flow rate. So you have to be on the lookout for your best efficiency point flow rate, so that you will know that this is the flow rate at which my pump will work at best efficiency. Now, if you look at the shape of the efficiency curve, it simply means that as you move away from the best efficiency point, right, the efficiency of the pump drops. As you move further away, either to the left or to the right, I believe you can see the shape of the efficiency curve, right? You can see the shape of the efficiency curve. Okay? So now, as you move away from this best efficiency point, so look at this. As your flow rate is moving away from the best efficiency point flow rate, the efficiency of your pump is going down. So the efficiency of a centrifugal pump is lower, of course, in shut-off condition, and at the same time is lower in in run-out regions. So that is why it is always advisable, or it's always advised to run your pump, very close to the best efficiency point flow rate. By the time we look at, we move to technical evaluation of the vendor data sheet, you will see what API 610 says with respect to the margin that has to be, or the percentage that has to be between your rated flow and your best efficiency point flow rate, okay? Or your best efficiency point flow rate between your best efficiency point flow rate and your preferred operating region. So basically, you will see on a centrifugal pump that efficiency curve. It is telling you, it's showing you the best efficiency point flow rate. That is the flow rate at which your pump, right, has the maximum efficiency. So if you are running the pump further away from the best efficiency point, you yourself, you know that you are already operating the pump away from the maximum efficiency. As you can see that the efficiency will keep on dropping, and you know that you know the effects on your pump operation. So when pump efficiency is maximum, it's called, of course, like I mentioned, it's called the maximum efficiency, or it's called the best efficiency point for a pump. So the BEP, like you see in some text, is usually specified on the pump curve itself. If not, if the best efficiency point is not specified, you have to contact the pump manufacturer to furnish the best efficiency point on the pump curve. All right, we ideally want our pump to operate, right, on best efficiency point, but it's not always possible, of course, because you cannot always run the pump at the best efficiency point flow rate. But it's not always possible due to, of course, due to variation in process conditions. There will always be variations in process conditions, so you cannot always be running your pump at best efficiency point flow rate. Therefore, depending upon your pump model or the design, the OEM, the original equipment manufacturer, publish a recommended operating regions between the minimum and maximum allowable flow. So they will recommend the minimum and allowable operating region. You can see the minimum allowable flow and the maximum allowable flow. So you can see your best efficiency point flow rate, because you cannot always be running your pump because of the variations in your process requirement. So your flow rate cannot be fixed. However, the OEM must furnish you the minimum allowable flow, and it has to furnish you the maximum allowable flow. By the time we look at some of the basic design condition as per API 610, you will see the margin in terms of percentage that has to be between your best efficiency point flow rate and your maximum allowable flow, or your preferred operating region. All right, so same way you will also have your power curve on your what? There will also be what? Power curve on your pump curve. You will see MPSHR curve. All right, so your power curve is another important element as far as centrifugal. You can see the power curve here, and you can see the shape of the power curve. You can see the shape of the power curve. Now, if you are operating your pump at a different flow rate, you can see how it directly affects the power requirement of the pump. So as you move further away from the best efficiency point flow rate for this given curve, you can see the effects on the power requirement. So the power requirement is going higher. So meaning that as you run your centrifugal pump further away towards the right, away from the best efficiency point flow rate, the power requirement to drive that pump is going higher. So the power consumption will be increasing. It increases with increase in pump flow. So while selecting a pump driver, we must consider possible operation range. So as a minimum, your driver has to be of larger pumps where sufficient flow control and monitoring is available. Drivers smaller than rated run out flow can also be chosen to save energy. You always want to save energy for your pump. So that is why you need to be able to do what? To know. You have to be able to tell yourself when you are operating further away from the best efficiency point flow rate, you should be able to know the effects on the power requirement for your driver. So you have to be able to size, or you must have selected the right driver for a given operating region. So all centrifugal pump basically can handle a range of different impeller size, ranging from minimum impeller diameter and the maximum impeller. This must have been specified on what? By the OEMs on the pump curve. So as per process requirement, I said impeller trim is chosen so that the pump can meet the rated point or the duty point. So the effects of the impeller diameter on pump performance area is what you can see on this. If you look at this different pump curve, you have maximum impeller diameter curve. You can see the rated impeller diameter curve. So if your pump is having the rated impeller diameter curve, is with a rated impeller diameter curve, the behavior of the pump will be based on this rated impeller diameter curve. Now, same way, the OEM will also specify in case you change the impeller diameter to the maximum impeller diameter in will have been given to you on the pump curve, will have been shown on the pump curve. The behavior of the pump will not be like the rated impeller. As you can see here, right? If the best efficiency point is here, now if your flow is at say 20 cubic meter per hour, is somewhere around here. If you are considering the rated impeller diameter curve, your head will be here for rated impeller diameter curve. But if you have a maximum impeller diameter curve, you see that the head, your differential head will be here. So you will see the effect of change of impeller diameter. So basically that is why the pump OEM or the pump manufacturer will show you the behavior of the pump as a result of changes in the impeller diameter with the diameter given. So in a nutshell, a pump performance curve is an important tool, is an important what? Is an important document which you need to predict the overall pump behavior, operating range. So you have to be able to do what? To able to analyze and understand some of this information provided on the pump curve, all right, in which I have talked about. So you can always go back and check your what? And check your pump curve and see some of this data. We are still going to look at a typical pump curve from a particular vendor in the course of this training session, right? And you will see some of these values and how you can determine whether it has satisfactorily met some of the requirements stated as per API 610 for the basic design conditions of centrifugal pump. All right. Now, next is another terminology which you have to be very familiar with, is the pump specific speed. There's no way you will talk about a centrifugal pumping system without mentioning some of these terminologies, and that is why I am taking my time to explain in details what each of these terminology and the effects on your pump operations. Because as a machinery engineer or as a process engineer, for you to be able to make the right decision or to make a sound engineering decision on vendor offers received, you must be able to analyze, you must be able to interpret some of the information, some of the language put by the vendor on their respective documents. That is where so many engineers get it wrong. And not only that, you have to be able to relate those information provided by the vendor on the datasheet to what is stated in API 610 basic design requirements. Is it in line with what is stated in API 610? If it is not in line with it, then you won't go ahead with the vendor. So if you have 5 vendors, depending on how any of them successfully met the requirement as per the international standard governing the design of the equipment, that is the one you will go with. On this channel, I've also discussed on technical bid evaluation for centrifugal pump. So if you are yet to see that video, just go through my channel. You will see how to carry out technical bid evaluation for, say, 10 vendor offers, right? So you see some of the information that you will look out for on the vendor's document to be able to do what? To be able to carry out some of this evaluation, so that you can determine, right? So that you can determine the vendor you will eventually go with. Because you can receive bids from 20 or 15 vendors. So without you understanding some of these terminologies and how you can relate it to what the standard governing the design of the equipment says, then what are you doing? Whatever the vendor supply to you, you just install it, and you see after 3 months, 4 months into operation of the pump, you see the pump developing all manner of faults that you have to do what? Stop the pump and carry out maintenance on the so-called pump. So that is why I have taken it as a duty to try and break down some of these terminologies, so that you have a better feel of what this is all about. And it's actually very simple. If you can take your time, go through don't just listen to my videos once and assume you know it. No, you have to go over it again and digest it. And I assure you, my email, you can always write to me via my email address, or you can send me a message on LinkedIn, or through any form. You can reach me, and I will definitely respond to any of your queries, right? So now we need to look at quickly on pump specific speed. What is pump specific speed? What is pump specific speed used for? You see, when you are selecting a centrifugal pump for any given application, right? When you are selecting a centrifugal pump for any given application, with you, of course, knowing your speed, with you knowing different parameters, there are some other parameters that you need to be very, very familiar with. And one of it is what? One of it is this pump specific speed. All right? So your pump specific speed is just basically a very, very important. Okay, someone, Ugochukwu, is typing a question. Please, is API 610 the acceptable standard for because a lot of European manufacturers are not API 610 certified very much. API 610 is actually the international standard right? Governing the governing the basic design, governing the basic design of what? Governing the basic design of centrifugal pump. I hope that has answered your question, Collins. API 610, API 610 is the international standard, is the American Petroleum Institute standard governing the what? Governing the basic design of governing the basic design of um centrifugal pump. All right, and that is what. So if you check through the API 610, you will see some of the basic design conditions that the pump vendors, right, needs to follow strictly. And some of this information provided as the basic design conditions must be, these are the things that you need to check for by the time you are carrying out technical evaluations of any offer received by different vendor. So when selecting a pump for a particular application, with you knowing parameters like the speed, the flow, the differential head, you also need a calculation of what? You also need a calculation of specific speed. As that is what we identify the impeller shape. We have different shape of impeller. So the calculation of this pump specific speed is what we identify the impeller shape most suited to the task. So now, like I mentioned, I said we have different impeller shape. So you need the calculation of your what? Of your pump specific speed, so that you can identify the impeller shape best suitable for a given task. Like you see, you have radial flow impeller, we have mixed flow impeller, we have axial flow impeller. So depending on the value obtained for the pump specific speed, you can see the pump specific speed. You will see in the course of this training session how you can determine your pump specific speed. If your pump specific speed is within a range of value, say 25 to 70, what has to be in your pump has to be radial flow impeller. That is the impeller that will be most suitable for that given application. So if your pump specific speed calculated is up to 160, say between over 70 to 160, it has to be mixed flow impeller. Same way, if you have, of course, 140 upward, say 140, 150, 160, then you can have what? You can have your axial flow impeller. So basically, there are three types of impeller, of course, based on the direction of flow with respect to the axis of rotation. You can see here the radial flow impeller, the flow is moving radially outwards the impeller, like you can see here. So depending on what you obtain as your pump specific speed, we are going to see how you can determine your pump specific speed, right? Depending on the value, then you will choose the type of what? The impeller shape best suitable for the task. So you can always check based on the process requirements, based on the process conditions which has been furnished to the vendor. What type of impeller shape has this vendor put on its mechanical data sheet? Is it the right impeller diameter shape? Is it the right impeller shape? So you can always verify with the calculation of the pump specific speed. Same way, you can have axial flow impeller with the flow, parallel to the axis of rotation. So of course, with the mixed flow in between the radial and the axial. So basically, the radial flow impeller the radial flow impeller is most suitable for discharging small quantity of flow against high head. So you also have to check, do you have a small flow, you have a low flow against high head? So if you have that case, then it's radial flow impeller best suitable for that task. Mixed flow impeller, they are most suitable for discharging large quantity of flow against medium head. Same way axial flow impeller suitable for discharging, you see, large quantity of flow against small head. So you see, if the specific speed is between this range of values, you can see the impeller shape most suitable for that task. Now, the pump specific speed is that design index, like I told you, that determine the impeller what? That determine the impeller shape, is the design index that determine the impeller type and the geometric similarity of the pump. So that your pump specific speed, or the NS, of course denoted as NS, equals your NS equals your N multiplied by your Q raised to power 0.5 over your what? Over your H, right? Over H raised to power 0.0.75. So each of these, so when you take your N is the rotational speed, which is expressed in what? In RPM. Your Q is that total pump flow rate, that your pump total capacity expressed in cubic meter per seconds. So if your flow rate is in cubic meter per hour, for you to use it in this expression, you have to convert it to what? That's another mistake that a lot of engineers make by the time they are calculating their pump specific speed. They use cubic meter per hour. No. In SI units, you have to put it in cubic meter per seconds, right? For single suction impeller anyway. But for double suction impeller, your Q will not be total pump flow rate. You have to use half of the total capacity of the pump to calculate your NS. Of course, your N I mentioned is the rotational speed expressed in revolution per minute, RPM. Your H here is the head per stage at the BEP. BEP is the best efficiency point flow rate, like I said, where your pump is, which is the flow rate at which your pump is having what? The maximum efficiency. So your H is the head per stage at the BEP at maximum impeller diameter, which is expressed in meter. So by the time you put these things together, the specific speed is derived using SI units with your N in RPM, with your Q in cubic meter per seconds, with your H in meter. You have to multiply it by 51.64 to get your specific speed in USC units. That is also very, very important. So that is how you obtain your pump specific speed. So with the value of your pump specific speed, if it is between say 25 to 70, you know that the impeller shape that is most suitable for that task, for that operation, is the radial flow impeller. If it is close to 160, then you know that it is best to use mixed flow impeller for that application. If it is around 150 up to even 400, it is what? Axial flow impeller. So basically, the pump specific speed will determine the impeller shape and the geometric similarity of the pump. Now, there is another terminology which you also need to do what? You also need to be, right, to also be familiar with, and that is the pump suction specific speed. Now, this is not pump specific speed. This is pump suction specific speed. Your pump suction specific speed, I need to mention this, is not to be confused with the concept of specific speed. Like I said, the pump specific speed, which is your NS, pump specific speed, is an indicator of the impeller geometry and discharge characteristics is an indicator of the impeller shape. All right, while the pump suction specific speed is an indicator of the impeller inlet geometry and suction characteristics. The pump suction specific speed tells you how aggressive your pump suction condition is. All right, so it's also very important for you to also obtain or to also calculate, check the pump suction specific speed, because it is a function of your MPSHR. The lower your MPSHR, you can see the higher will be your pump suction specific speed. All right, so the NSS, which is the pump suction specific speed, is expressed with by N multiplied by your Q over raised to power 0.5 over MPSHR. Like I said, your N is the rotational speed expressed in RPM, while your Q for this case is the flow rate per impeller I expressed in cubic meter per second. Okay, your Q will be total flow rate for single suction impeller, and it will be what? 1/2 the total flow rate for double suction impeller. You need to also take note of that. And of course, your MPSHR, which is the characteristics of your pump obtained from the vendor by the test conducted by the vendor, right? So you put this together to obtain your what? The pump suction specific speed. So the pump suction specific speed is an indicator of the what? The impeller inlet geometry. It shows you, it tells you how aggressive, how your pump can withstand, see, some of these losses that occurs at the suction or at the inlet of your pump. So it's also very important to look at some of these parameters and check whether the NSS obtained, whether the suction specific speed obtained from a given pump manufacturer is in line with the conditions stated in API 610. All right, so this is where I'm going to stop for today, and I hope you have been enjoying this session. So if you are yet to subscribe or you are yet to share with your friends, please share with your friends and let us tell our colleagues at work, you understand, to take, especially those that have interest in rotating equipment, to subscribe, like, and comment. So thank you very much for your time. So today, this will be the end of this session. Thank you.